Hello, pre-cal. It's so exciting. We're looking at the rational root theorem. Yay! All right, so I am going to let the letter Q represent the leading coefficient. And I don't want anyone to have a freak out attack. I'm going to explain to you exactly what I'm doing, just like I always do. Okay, I'm just letting the letter Q represent the leading coefficient. I'm letting the letter P represent the constant in a polynomial. Okay, so I'm just going to use these to illustrate what the rational root theorem tells me. Now, if you'll recall in the last video, I told you that the rational root theorem gives you a list of possible rational roots that we can find using the constant and the leading coefficient. So if you will look at this fraction right here, I'm going to create a fraction of P over Q. So what that means is I'm going to let P represent the constant factors and Q represents the leading coefficient factors, and you'll notice it's all plus and minus. All right, so having said that, I'm going to look down here at my polynomial. Well, 2 is my leading coefficient and 6 is my constant. So if I let the constant be represented by the letter P and the leading coefficient represented by the letter Q, what I'm going to do here is create a fraction of P over Q. And that's going to be equal to plus or minus, and then I'm going to create a fraction. Now, a lot of students forget this, but it is important. You need parentheses around that fraction bar because the plus and minus extends to the entire thing. All right, so in my numerator, my constant is a 6. A 6 consists of the following factors. We've got 1, 2, 3, and 6. Those are all the numbers that can multiply to give me 6. 1 and 6 multiplies to give me 6. 2 and 3 multiplies to give me 6. I'm going to do the same thing in the denominator with the lead coefficient. Well, the lead coefficient is 2. Well, there's only 2 factors of 2. 1 and 2. So I'm going to tidy this up a little and write these all out as a list of numbers. And I'm going to write them in ascending order. So my very first answer is going to be 1 over 2. And then I've got 1 over 1. And then I would have 3 over 2. And then 2 over 1. And then 3 over 1. And then 6 over 1. I don't have to include 6 over 2 because that reduces to 3, which I already have listed. All right? So if you struggle with that, here's what you can do. Okay, you could do it this way. Okay, I've got 1 over 1, 1 over 2, 2 over 1, 2 over 2, 3 over 1, 3 over 2, 6 over 1, 6 over 2. And then you can just reduce those and get rid of your repeats and put them in order from least to greatest. Okay, so let's do another one. All right, look at this example right here. My leading coefficient is 2. My constant is 3. So P over Q equals plus or minus 1 and 3 over 1 and 2. So I'm going to have 1 over 1, 1 over 2, 3 over 1, 3 over 2. I'm going to put that in ascending order. And that gives me 1/2, 1, 3 over 2, and then 3. All right, so what does this mean? This means that I have 8 possible rational roots for this particular polynomial. Now, I want you to think logically about this. This polynomial is in a degree of 4. So how many total solutions does it have? Well, it has 4 total solutions, but the rational root theorem will give me a list of possibilities to start with. This is going to make more sense when we move into 2.5 of this Unit 2. All right, so let's do the next example. My leading coefficient is 3, my constant is 4. Okay, 4 consists of a 1, a 2, and a 4. I don't have to write the 2 again. 3 is 1 and 3. So again, I'm going to write out all my possibilities. So I've got 1 over 1, 1 over 3, 2 over 1, 2 over 3, 4 over 1, 4 over 3. And then I am going to put these in order. All right, so I've got 1/3, 2/3, 1, 4/3, 2, and 4. There we go. So again, notice that the degree of this polynomial is 3. Well, I've only got 3 solutions, but clearly there are more to choose from because I have 1, 2, 3, 4, 5, 6 total, and if I'm looking at plus and minus, that's 12 possible rational roots. That's just a choice to pull out of. That's just a choice pool to choose from. All right, so I want to make some notes about some complex numbers. We talked about complex numbers in the previous video, but I want you to remember that anytime we're taking the square root of a -1, your answer is I. That stands for imaginary. This means that there is also going to be another root of -I. Why is that, Miss Griggs? Because remember what the rule for taking the square root is. If I take the square root, I'm taking plus or minus. So anytime I'm taking the square root of a negative, I'm going to have a positive I and a negative I. All complex solutions occur in conjugate pairs. That's what these are called. Okay? Conjugate pairs. This is what it will look like. If -2 plus 6i is a solution. This is just an example. So let's say I tell you that for a particular polynomial, -2 plus 6i is a solution. Well, I can name one more solution based on this. The conjugate pair of this would be -2 minus 6i. That's what it means to be a conjugate pair, because the sign for I need a positive one and a negative one. Notice that the 2 is negative in both of these solutions, but that the I has a positive and a negative. So in these examples, if I give you one solution and it has an I in it, you should be able to come up with another one. Because if you've got one solution with an I, there's going to be another solution with an I. So if one of your solutions is positive 2i, then another solution is negative 2i. If one of your solutions is 2 plus I, another solution is 2 minus I. If one of your solutions is -3 minus 4i, you guessed it, one of your other solutions is -3 plus 4i. If one of your solutions is -3i, another solution is positive 3i. So hopefully you understand that the i's come in pairs just like your i's. All right? So list how many possible rational and imaginary roots you could have for a given polynomial. All right, I want you to notice that this polynomial has a degree of 7. This means that there are 7 solutions total. Now, some of those solutions could be real numbers, some of them could be imaginary numbers. We're not sure, but I am going to list how many possible real and imaginary roots we could have. All right, what you have to stop and think about here is the idea that I cannot have one imaginary solution. They have to be in pairs. So here's the deal. I can have 2 imaginary solutions, or 4, or 6, because those come in pairs. Are you with me? So that means that in a degree of 7, I'm going to list how many real solutions I could have versus how many imaginary solutions I could have. Well, here are the choices. None of them could be imaginary, or 2 of them, or 4 of them, or 6 of them. Those are my only options. So if 0 of them are imaginary, that means all 7 would be real. If 2 of them are imaginary, that means I could have 5 real solutions. If 4 of them are imaginary, that means 3 can be real. And if 6 of them are imaginary, that means I can have 1 real. So this is just a list of all the possible combinations of real and imaginary numbers I could have. I could have 7 real, no imaginary. I could have 5 real and 2 imaginary. I could have 3 real and 4 imaginary, or I could have 1 real and 6 imaginary. Those are the only possible real and imaginary combinations I can have for a polynomial in a degree of 7.